Okay, now for what you have to do. We are going to graph each one of these. We're going to find those pieces, and then we are going to graph the inverse after we find it. So let's graph this one first. 7 to the x is growth. Looks about like that. The 2 in front is going to stretch it. Takes 1 0 up to 2 0. That number in essence stretches the graph up and creates a new y-intercept right there. Plus 5 is going to shift it left, 1, 2, 3, 4, 5. Minus 6 is going to shift it down, 1, 2, 3, 4, 5, 6. The asymptote was here. It also gets shifted down 6. So there's the asymptote, and there's the stretched out graph. The asymptote is now at, it's lazy at y equals -6. It has a vertex at left 5, down 1, 2, 3, 4. So -5, comma 4. The domain of this guy right here, the domain is going to be from -infinity to infinity. And the range is going to be, starts at -6 and goes up forever to infinity. Alright, now I'm going to find the inverse, which I'll do in a different color. I'll do this in blue. I'm going to switch the x and the y, which is right there. So those two are going to switch. X equals 2, 7 to the y plus 5 minus 6. The first thing I'll do is I'll move the 6 over. The next thing I'll do is I'll multiply by 1/2 to get rid of the 2. And I get 7 to the y minus 5 equals 1/2 of x plus 6. Alright, I gotta get the variable out of the exponent spot, so I'm going to pigtail it. I'm going to go log base 7 of 1/2 to the x plus 6 equals y minus 5. Usually that's on the other side, but the two sides are flip-flopped, and I still did pigtail it. That number to that power, or that number to that log equals that value there. So I'll add 5 over, and I got an inverse of y equals log base 7 of 1/2 x plus 6 plus 5. That should be the inverse, which again we have f to the -1 is the inverse notation. That should be the inverse of the original graph. So I will graph a log graph, and let's go through the pieces. 1/2 shrinks it horizontally, which would make it even a little bit steeper. It would actually go through there, go through the 2. Shrinks it down by a factor of 1/2. That's basically what I did. Plus 6 minus 5 is going to shift it left 6 and, oops, this was a plus, so that's a minus, and that should have been a minus. So it's going to shift it left 6 and down 5. So I'm going to take this dot here, I'm going to go left 1, 2, 3, 4, 5, 6, and down 1, 2, 3, 4, 5. That will put it there. It's still the same shape. Asymptote goes left 6 also. 1, 2, 3, 4, 5, 6. So the asymptote would be sitting over here. And then I would have a graph that looks like this. You can see they are reflections over the line y equals x. Alright, so this one's asymptote is, well, the vertex is here at -4, -5. That should have been -4 also. -4, -5. That one's vertex. This one has an asymptote at x equals -6. That one was y equals -6. This one is x equals -6. This one's domain. It goes from -6 to infinity. And this one's range, it goes up and down from wherever, -infinity to infinity. And what we can see is we can see that those two are the opposite of those two. We flip-flop them around. And my vertex has flip-flop values. Everything looks good. We can go to the next one. Okay, log base 5 of x minus 4 plus 7. I'll graph log base 5. Log graph. minus 4 right, 1, that dot goes right, 1, 2, 3, 4, and up 7, 1, 2, 3, 4, 5, 6, 7. It should be right there. A log graph, the asymptote would have bumped over 4 also. So here's my asymptote. There's what the graph looks like. Find the inverse. I'll switch the x and the y. This is the y. I'm going to switch the x and the y around. So I'll put it x equals log base 5 of y minus 4 plus 7. And I'm going to find the inverse by moving the 7. Okay. Pigtail it. Add the 4. 5 to the x minus 7 plus 4. So I'll graph this one now. Growth graph. 5 to the x is growth. Minus 7 shifts that dot to the right 7. 1, 2, 3, 4, 5, 6, 7. And up 4. 1, 2, 3, 4 to there. The asymptote was here. It would have also shifted up 4 to here. And my graph would have looked like this. And it's still a reflection over the line y equals x. You can still see it. This one's a vertex here. Oh man, it's off the graph. 5, 6, 7, up 1, 2, 3, 4, 5. So it looks like it's at 7, 5. I don't even really need to know. I can just make this one's vertex at 5, 7. This one's asymptote was lazy at y equals 4. This one's asymptote was excited at x equals 4. This one's domain goes from, this one's domain, the red one now, the red one, up and down, well, left and right forever rather, negative infinity to infinity, and the range goes from 4 to infinity. And this one down here, this blue one, the domain on that one, it starts at 4 and goes to infinity, and the range, it does go up and down forever from negative infinity to infinity. And we can see once again, hey, everything here is flipped over here. Okay, last one, ln works exactly the same way. I'll do this one in blue. Log graph, left 3, up 3. That dot goes left 1, 2, 3, up 1, 2, 3. So left 1, 2, 3, up 1, 2, 3, and then the asymptote would have slid over to here. So it looks like this with an asymptote at x equals negative 3. The vertex is negative 2, comma, up 3. The domain, it goes from negative 3 to infinity, and the range, it goes up and down forever, negative infinity to infinity. Okay, let's switch it. ln is the same as log base e. I'm going to switch the x and the y, and that's x. Okay, so I'll move the 3 over. And I'll pigtail it. And I'll move the 3. And I'm going to graph that guy. So I go like this. That dot goes right. 1, 2, 3, and down. 1, 2, 3. So it's right there. I will put my asymptote in, draw the graph in. They look like mirror images over the line y equals x. All of these get flip-flopped. 3, negative 2. Y equals negative 3. Negative infinity to infinity. And then the range is negative 3 to infinity. What you have to do is the exact same thing on this sheet.